equals 1 to infinity of, AK, EK. Goodness gracious. All right, getting to the point here, eventually. No. That's the... Right, so that's the dense. I mean, dense is freeing us to adjoin limit points of sequences of finite linear combinations. I mean, so it's not, I don't think it's saying that everything in H can be built from a finite linear combination of the basis. That's not a sufficient, that concept won't work. We need series of things to build things in H. And I think that's what's meant here, this dense. And then theorem 2.3 gives 4 equivalent characterizations of a, and so this is definition of an orthonormal basis for a Hilbert space. Right? So the notion, our previous notion of spanning isn't quite good enough, right? I mean, like our notion of basis before, like I don't know, we never really talk about a basis in infinite dimensions that much or at all in my linear course. But in this context, the notion of spanning has to be, finite linear combinations aren't going to quite make it. We have to allow infinite linear combinations. One of the equivalent characterizations of it being a basis is if AK, this is point number 4, if AK is the inner product of F with EK, then the norm squared of F is equal to the series K equals 1 to infinity of the coefficients. And in fact, also, by the way, if the inner product of F with every an arbitrary element of the orthonormal basis is 0, then it means that vector is in fact the 0 vector. So if you look at theorem 2.3, we still do get a lot of what makes an orthonormal basis in finite dimensions work as it does, right? All right. So he then, the proof of this theorem that I'm just quoting, 2.3, in the proof of that theorem, he discovers Bessel's inequality. All right, Bessel's inequality. Bessel's inequality, instead of this, we put greater than or equal to that way. This is Bessel's inequality. And then later, this equality actually has a name that is known as Parseval's identity. All right. And then theorem 2.4 says any Hilbert space has an orthonormal basis. Whoa. That's really nice, right? Any Hilbert space has an orthonormal basis. And then he goes on to define what does it mean for a mapping to be unitary, which is the natural generalization of the notion of unitary map that I define in like linear. It's a map which preserves the complex inner product in a natural way. And then it's kind of boring. Any 2 infinite dimensional Hilbert spaces are unitarily equivalent. So essentially up to a unitary transformation on a infinite dimensional Hilbert space, they're all L2n. they're all square summable sequences, or they're all L2Z. So, and yet that's not to say that different Hilbert spaces aren't interesting for different reasons, as is made exceedingly clear in these books, as a large portion of these books is expositing the structure of Hilbert spaces as it appears in different contexts. He next defines a pre-Hilbert space, which is like a Hilbert space, except it lacks completeness. The quintessential example of that would be Riemann integrable functions from minus pi to pi. You have to throw in something extra to get a Hilbert space. That's called a pre-Hilbert. Pre-Hilbert space is like Hilbert space, but drop the completeness assumption. Let's see here. So at this point, I wanted to skip back to volume 1 and give you the preamble to Emily's talk. So all of these things that we've been studying really, in some sense or another, go back to the discovery of Fourier in the early 19th century that the heat equation could be solved using, well, what we now call Fourier series. And then as they played with these things a little bit more, they realized that there's a deeper way of looking at solving PDEs. Basically, we can use something called the Fourier transform to solve partial differential equations. And so I'm just going to write down just some of the very rudiments of this idea. So, for example, if I have a function that goes from A to B, and so A to B, I think to the complex numbers, then this gets Fourier series. The Fourier series is this, come on. Well, Fourier coefficient, rather, f hat of n, 1 over L. The integral from, that L is b minus a. Emily, is that right? Yeah. F of x e to the minus 2 pi I n x over L dx. This is for n and z. So this is the so-called Fourier coefficient. Turns out you can, I think typically this is just called a sub n, right? Later, we soon start calling that a sub n. Am I wrong? Am I wrong? And then so, let's see here. And so if we, I don't really want a to b. I want minus pi to pi. That probably makes this L what? 2 pi, right? Oh, well, if I do that, then everything's going to start canceling. I mean, if we put L equal to 2 pi, then this 2 pi cancels that 2 pi. And, well, that's fine. Let's do it. 2 pi, it's prettier if that way, right? Minus I n x. All right. And then he says f of theta, because he's thinking of theta is this. And I said this means almost everywhere, but that is incorrect. That means it's the Fourier series of f. It's even more loaded than that. Like this means Fourier series generated by f. Stop your whistling, Sprano. I know it's Sprano when I know it. Here. Anyway, so that is the so-called Fourier expansion. Now, fun example. If you look at f of theta equal to the absolute value of theta as your function, look at the Fourier expansion of this. It has an pi over 2 n equals to 0, or minus 1 plus minus 1 to the n over pi n squared if n not equal to 0. So he says put theta equal to 0. What does this give you? We get absolute value of 0 is equal to the sum. Well, what's this sum collapse to? Yeah, the pi over 2, right? From that, and then n not equal to 0. And let's see here. So think about that. Either n is even or n is odd. If n is odd, what happens here? You get minus 1 plus 1, right? Or wait a minute, no. Oh, n is even. N even I want to look out for. N even is bad, right? N odd, though, gives me what? Yeah, minus 2 here, right? So we could rewrite this as minus 2 over pi times 2k plus 1, right? K equals, 0 to infinity. And then the same, yeah, I'm trying to think how to, can I just put a 4 there? Yeah, I think I just put a 4 there. And so you see that this implies that pi over 8 is equal to 1 over, and this is squared, right? 1 over, 1 plus 1 over 9 plus 1 over 25 plus 1 over 3, I see, 1 squared, 3 squared, 5 squared, 49. So the sum of the odd squareds is pi over 8. He claims you can derive the p equals 2 series in the problem, but I'm not seeing it right off. I mean, that must involve some kind of like, how do you get the even terms? Maybe like a shift of variable or something. I don't know, but there's a little trick to get the even terms, but yeah. So anyway, this is one of the things that's exciting about Fourier series is it allows us to derive things that like Calc 2 doesn't quite get us to. But then, here's what's really interesting, I think. And maybe Emily will make this more clear in her talk. I don't know. Maybe not. And if not, that's okay. What I'm really doing at the moment is advertising a course I haven't taught yet, which is the Fourier transform. What's the Fourier transform? Well, f hat of, I'm going to use k. Well, I'll use p. Integral from minus infinity to infinity of f of x e to the minus 2 pi I xp dx. So this, something like this, f is f of f equals to f hat. This is the Fourier transform. It trades functions of position for functions of momentum. You could think about P as being momentum. All right. And it has many properties, but here's the two most interesting one in proposition 1.2. To me, the two most, perhaps the most interesting property is that the Fourier transform of the derivative of f is actually equal to 2 pi I p f hat. And vice versa. If you have the Fourier transform of minus 2 pi I xf, well, that gives you df hat dp. So multiplication becomes differentiation, and differentiation becomes multiplication. But there's also this complex I floating around, having its way with your intuition. What's that? But the transform is linear. Just make like 2 more comments and we'll be done. If you have f of x as a Gaussian, this function has the distinguished pleasure of this. In other words, the Fourier transform of f is equal to f again. Like it doesn't, Gaussian is unaltered by the Fourier transform. There's something called convolution, which you've already seen in Laplace transforms, but that's a more general notion that extends to all integral transforms. You might say, what are good examples of integral transforms? Well, Laplace transform and Fourier transform. Other than that, I don't know. I guess there's the Legendre transformation. That has something to do with phase space in quantum in classical mechanics. But anyway, I think it's really just the Laplace transform. Anyway, what do I know? Not that much. So this is convolution. Convolution takes it's the next best thing to a homomorphism in this world. The Fourier transform of the convolution is the product of the Fourier transforms. It's very nice. There's a theorem by Plancherel which says that if f is in the short space, then the norm of the Fourier transform is equal to the norm of f. We've already seen a close cousin to that in the statement about the orthonormal basis, in some sense. Now I'm being fuzzy. And finally, I leave you with this example. So we want to solve a heat equation. Partial u partial t equals to partial squared u partial x squared. So what you do is you take the Fourier transform of this partial differential equation. Take the Fourier transform. And when you do that, you get partial u hat partial t equal to minus 4 pi. See why there's a minus 4 pi squared? P squared u hat but that's a linear differential equation in time, so you can just separate and integrate. And so we've traded that for u hat is equal to some a, doesn't really matter what that constant is, e to the minus 4 pi squared p squared t. And so then, to get the solution back, you want to take something like the inverse Fourier transform. And it turns out in the process of doing that, you incorporate the initial heat distribution for the problem. In particular, theorem 2.1 tells us that the solution, u of xt, is equal to f convoluted with the heat kernel, ht, of x, where ht is the heat kernel, quote unquote. And this solves the heat equation, but this is coming from taking the inverse Fourier transform of that u hat, truth be told. And here, if you're wondering what f is, you're given that u of, u of x0 is equal to f of x. That's the initial temperature distribution for the heat equation. And so, I mean, this has been known in some sort of sloppy heuristic way since the beginning of the 19th century, but it's taken us the better part of the last 150, 200 years to flesh out the analysis of this. It does look a lot like the Gaussian distribution, doesn't it? Yeah. Well, I mean, I think it does look like a Gaussian, yeah. I mean, that's part of this story, is building other things from Gaussians or something like that. I shouldn't say more. I don't have it all, settled for myself, but I find this to me it's a very interesting, we teach you how to solve ordinary differential equations with the Laplace transform in 334, typically. But we might touch on Fourier transform if you're lucky. If I'm really on my game, I'll spend a half hour on it. I know one nice example that I can show students, but it's actually a very general technique. But the thing is, what's the class of functions which survives the transform? For what kind of function can you take a Fourier transform of it and it gives you a function which is still integrable? So what I was just talking, by the way, this is all from volume 1 of Princeton Lectures and Analysis, And so in this volume 1, he develops the Fourier transform on a more special more special space function called Schwartz space, which is functions of rapid decrease, And then as the books go on, he loosens the reins and develops he shows how the Fourier transform extends to wider and wider classes of more exotic functions. The book we've been spending most of our time on, volume 3, is still just a step on the journey to volume 4, which finally picks up the story with the study of distributions, right? Which is an even more nuanced way of looking at and understanding the equations which naturally appear in mathematical physics. If you take a course in junior level electromagnetism, you'll find that most of the solutions are written in terms of something called the Dirac delta function, which is, what's that? Is the course offered here? I don't know. I'm not sure what they offer in the chemistry department. Maybe there's a quantum physics in chemistry, right? Could be. I don't know what the chemists are doing, so I can't say to a certainty it's not being offered. But anyway, these Dirac delta functions are actually distributions, and the real analysis of it is actually quite involved, and it would take me several courses to. What I've learned, Emily, and I'm so happy about this, is that to really understand the Fourier transform, it's so much more than another couple lectures I'm not giving in differential equations. It's so vastly deeper than that. And just glancing through these books the last few days has made it clear to me my abject ignorance. I have so many things to learn, oh my goodness. Anyway, so that seems like a good place to end a course. Right where we started, right?